All right, before I get going today, I want to give you a quick rundown of the schedule of important events for the rest of the semester. I'll have the email out about this too, so you'll have it in writing, or so you don't have to necessarily scribble this down furiously. But just to give you a heads up for what's coming, because we do have a pretty furious finish to the semester, as you'll see. All right, so basically we have today's normal class, and then so this week and next Monday, so 4/17, and that would be next Monday is the 22nd. Thank you. Those are going to be normal class periods where we'll be going over the last remaining new material. This week, the 19th, as we said, is midterm 3 review. The questions for that are already posted in Blackboard, and that's going to be 1 to 3 p.m. in here. All right, so that's going to be the midterm 3 review, and then starting a little bit out of order here, but then 4/24, which is next Wednesday, that's going to be the first part of the final exam review. So for the first part of the final exam review, which is going to be on the 24th, I'll go over some of the topics from the past that I feel like we had the most trouble with. You're welcome to request topics to me ahead of time if there's something you want me to cover. And then I will also go over probably the first 6, I'll give you the exact breakdown in the email, but probably the first 6 or so questions of the final exam review that I'm going to prepare. I don't prefer to split up the final exam review into 3 sessions, but as I'll tell you in a second, we're doing course evaluations on the last day, so I wasn't able to fit all of it into 2 sessions. So that's the reason for that. So then 4/26, which is the following Friday, is going to be the second part of the final exam review. And that's going to be just going over some subset, about half of the questions or so in the final exam review. And that's going to be, again, 1 to 3 p.m. in this room. And then the last day of class is the 29th, and that's going to be final exam review part 3. Again, doing it in 3 parts this year because of also on this day we're going to do course evaluation. So if you want to air your grievances, make sure you're there on the last day. So it'll be final exam review plus course evaluation, so that class will be about 1 hour, and then the last 15 or so minutes, however long it takes to do evaluations, that's what you'll be doing, and I'll have to leave during that time. The choices were either to do it then or to do it during the 3rd midterm, and during the midterm exams you guys don't often come and you're in foul mood, so I decided to do the course evaluations on the very last day. So that's going to be the schedule. As I said, I'll have an email about that, so you don't need to, and I think that's accurate, but some of this is a little bit subject to change. Depends on whether we actually finish the new lecture material in the time that I have allotted for it, or if we have to go over a little bit. We might have to break up the final exam review in different ways, but we will have all of this before the end of the semester. Okay. So what we're going to talk about today is the last set of topics that are going to be covered in the 3rd midterm. So again, we have basically back-to-back exams, 3rd midterm and final in consecutive weeks. The 3rd midterm, we're going to finish that material today, and the last major topic for that is the structure of crystalline solids. And the types that we're going to really talk about in detail in terms of their structures are going to be metals, as we'll see. And then we'll also talk about ionic compounds, but that won't be covered until the final exam. All right. So the first one I'm going to go into is just a quick background of how we determine these structures. So these are, precise 3-dimensional structures that, relate that show the. I feel like I'm missing part of my graph. Maybe not. Anyway, they're precise 3-dimensional structures that show the positions of atoms in crystals. We talked a little bit last time about some of the terminology associated with that. You have lattice points, which are the atoms or molecules in the crystal. The lattice is the 3-dimensional, forever repeating system of points made up by those. And we're going to learn today some more details about how we define those structures and some of the characteristics of them. So the way we determine them experimentally is using X-ray diffraction. And so basically in this experiment, you shine X-rays onto a crystal. So you could do this with basically anything that has a crystalline structure. You could take a salt crystal from your kitchen and do this if you wanted to, or anything more interesting that you would prepare in a lab. So X-rays scatter off of the atoms in the crystal is basically what happens. So you take the X-rays, so here's your source, your X-ray beam, you shine it onto the crystal here, and then you get diffracted X-ray beams that come off at different angles. And what you're basically detecting is these little spots here on this plate. You see these little black dots everywhere. Those are the positions of the diffracted X-ray beams. So that's kind of what the measurement is. The spots on the plate represent where the X-rays constructively interfere. Because as is the case in any diffraction experiment, we talked about diffraction a little bit earlier, but it's not a major topic for us in this course. You may have seen it in physics class, but when you have diffraction, you get these diffracted beams that can either constructively or destructively interfere. They either align with each other and you have constructive interference, or they align with each other out of phase and you have destructive interference. And what you're able to detect are the places where you have the constructive interference. That's what these little black dots represent. As the X-rays come off at different angles, you detect them on this sort of photographic plate type detector, or there's more modern ones now that are more advanced than that. And then what you basically do is you take your crystal and you rotate it in all different directions, and you measure these diffraction patterns, as they're called, at all directions. We're not going to hold you guys responsible for the technical details of this, but we just want to give you the background of where we're getting these structures for that we're going to cover today. So then how you process this data, so that's how you collect the data. It's X-ray diffraction, it's diffracted X-ray beams. And then the sort of the theory behind how you process or interpret the data is called Bragg's law. So basically, as we're showing here, lambda is the wavelength of the X-ray beam that you use. And the reason that X-rays work so well for this is that the wavelength of X-ray beams tends to be similar in magnitude to the spacing between the atoms in the crystals. The reason this is so effective is because the wavelength of the X-ray and how far apart the atoms are roughly similar to each other. So the most common X-ray sources for these experiments use X-rays generated from molybdenum, which is a metal, and those X-rays are about 0.71 angstroms in terms of their wavelength, and that's roughly the radius of a carbon atom, for example. So they're pretty similar in size to the atoms that make up all these materials, so that's why this works so well. So that's what lambda is in this Bragg's law. Fun fact is that Bragg's law is actually named after two people named Bragg. It's a father and a son. I believe it's the only father-son duo to win the Nobel Prize. So I played baseball with my dad. They won a Nobel Prize together, so I guess they had a pretty nice life in that regard. But anyway, Bragg's law is defined in terms of the wavelength, and also some other parameters that are important. You have theta is the angle of incidence. So basically what we're doing is we're rotating the X-ray beam itself, or more often experimentally the crystal itself, so that there's a different angle between the X-rays that come into the crystal and the surface of the crystal. So you're rotating this around and getting different angles of incidences. And then the output that we're interested in is d, which is the distance between planes of atoms. Because as we said, these crystals are lattices of repeating points, atoms or molecules that repeat over and over and over again. So you're going to have these regular distances between atoms. You can define planes that involve sort of two-dimensional slices of your crystal. And what you're measuring is the distance between those planes, and that's what this d refers to here. And so that'd be the distance there is d, distance between the planes of atoms. And then what comes out of this then is the Bragg equation. This is what they basically got their Nobel Prize for, which is n lambda is equal to 2d sine theta. So the only thing I haven't defined is n, which is an integer. So you get what's called higher order diffraction. You don't just get one diffraction peak. You get higher order diffraction where it's some multiple n of this equation, but it's always an integer multiple. And so basically what you do in this experiment is you control theta, so you change the angle between the X-rays and the crystal, and then you measure the positions in terms of where you observe X-ray spots, and then you're able to back out d, which is the distance between those planes of atoms that correspond to that X-ray spot. So you basically measure a whole bunch of these, and with all these different d values that you measure, all these different distances between planes of atoms, you can piece together a three-dimensional structure. It's obviously way more complicated than what I described. There's a lot of math that goes into it, beyond just the Bragg equation. We're not actually going to use the Bragg equation in this course, by the way, so you don't have to do any calculations with it. But this is the condition for X-ray diffraction. It's when some integer multiple of the X-ray wavelength is equal to 2d, where d is the distance between the planes, times the sine of theta, where theta is this angle of incidence between the plane and the X-ray. So all this goes into basically some combination of angles and distances are used to measure the positions of atoms in a crystal. And it's a whole lot of math beyond that, and especially to know, which atom is which. So if we have sodium chloride and we have sodium and chlorine in the crystal, how do we know where the sodiums are versus where the chlorines are? That comes into play with the intensity of the diffracted X-rays, which is a whole other piece of the puzzle that we're not going to cover. But those are sort of the bare bones essentials of how we do X-ray diffraction, and we use that to determine three-dimensional structures in crystals. Now, the types of structures we're going to talk about in most detail are all cubic unit cells. So we said last time that a unit cell is the smallest piece of a crystal that you can generate the entire structure from by just translation, basically taking that piece and stacking it in all directions. And the types that we're going to talk about in this course are all have cubic unit cells. So the unit cell, which is that smallest repeating building block, is a cube. Think of it like a literal block that you would play with when you were a kid, and then you build the whole crystal by taking that cube and stacking it in all directions. So when we have these cubic unit cells, which are sort of these artificial cubes that we draw through part of the crystal, we can put atoms in different places in the cube. So they can there's all these different locations where we can place atoms. And what we want to be able to do at the outset is count how many atoms there are in that unit cell based on where their locations are in that imaginary cube. So one way we can do it is we can put an atom directly at the center of the cube, so one that is completely enclosed by the cubic unit cell. So we call this a body center position. Typically in cubic structures, it's right in the center of the cube, although really any position where that atom is completely enclosed by the cube would be considered body-centered. And when that is the case, when we stack the cubes next to each other, this atom is only enclosed in that one unit cell. It's not shared by other neighboring unit cells. It's just inside of that one unit cell. So this counts as an entire atom, one full atom. So these body center positions are not shared between unit cells. And so when we're counting atoms that reside in these body center positions, we count them as one full atom in the unit cell. Okay? Now we have other positions as well that would end up being shared by neighboring unit cells. Because remember, this cube is just one unit cell, and the crystal is actually this unit cell stacked on top of itself over and over again. So if we put an atom on the side of the unit cell, right on the face center as we call it, when we stack the adjacent cubes, this is going to be shared by one that's next to it, in this case to the left as it's drawn here. So the unit cell that's to the left of this one that's drawn is going to share this atom that's at the face position. So any two faces in a cube, when you stack them together, are going to be shared by two of those. And so this is going to be shared by two unit cells. And then so when we count it, when we're counting atoms in this unit cell, it's going to count as 1/2. All right, so any atom that resides on the face of a cube in a face center position is going to count as 1/2 of an atom when we're counting the number of atoms that are in that particular unit cell. All right, edge positions, and we also have those. Those are going to be shared by 4 now, because we're going to have basically one in each direction, 90 degrees. So you're going to have this cube that's drawn, you're going to have one over here, and then one sort of coming towards you that's harder to visualize. So the edge positions are shared by 4 unit cells. If you have cubic blocks at home, or you have little siblings that do, probably not yourself anymore, but you can stack these and see that every edge in the cube is going to be shared by 4 when you start lining them up next to each other as close as you can. So they're shared by 4, and because of that we count it as 1/4. We won't see edge positions today for any of the metallic crystal structures that we're going to talk about and that you're responsible for the third midterm. When we talk about ionic compounds, some of those have edge positions occupied, so those are going to count as 1/4 when we see those. And then finally, the last position, which is always going to be occupied in a cubic unit cell, as we'll see today, is putting one right in the corner of the unit cell. And in that case, you're going to be sharing it with 8 different unit cells, because you're going to have the 4 that are in sort of the same layer as this one, and then also 4 above that are stacked on top of it, that all would share that one corner. All right. So this section, as you'll see, requires a bit of three-dimensional visualization, similar to what we had in Chapter 4, probably even more complex. So trying to picture these in different ways is going to be helpful. And anyway, when you have a corner, it's shared by 8 unit cells, and as long as you know that that counts as 1/8, that's the sort of key piece of information that comes out of this. Okay? And as I said, every cubic unit cell is going to have, at the very least, atoms in the corners. Not all the positions will always be occupied. As we'll see, there's different combinations of these that we'll use. So this is called an edge position. I should write these out. And this one is called a corner position. So these are the different positions where you can place atoms into a cubic unit cell, and depending on which combination of those are occupied, we would count different numbers of atoms as being part of that unit cell. So that's kind of the first basic piece of information we need. Now what we're going to go through then are the different types of cubic structures that exist. So as I said, there's different combinations of these that are going to be involved, and there's going to be 3 cubic unit cells that you're going to be responsible for knowing some of the details of. Not all the details, but some of the key details. So the first one is called a simple cubic structure. And so what we have a few different ways of visualizing this. So one way to visualize how these structures are generated, at least, is to think about how different layers of atoms can be stacked in different ways to generate these regular repeating structures that have these different types of unit cells. So let's talk first about how we use layers of atoms to generate the simple cubic structure. And this one is fairly easy to visualize in terms of layers. So what we do is we start with one layer of atoms that's shown here in blue. So we start with a layer where all the atoms are all adjacent to each other, all of them touching, if you want to think about it that way. Now you'll notice that the specific way that we arranged this layer was we had one row of atoms, and then the next row is directly below that. So all the rows are eclipsed relative to each other. So it's a row and then a row directly below it. So if you have, again, you think of these like little marbles, you can stack marbles in this way. And then what you do is you take this layer and you just stack it on top of itself over and over and over again. So this stacking is the simplest, where you just take the same exact layer, you don't stagger it at all, it's just directly on top of the layer below it. So the individual layers then are going to be stacked directly on each other. So it's the most useful way, though, to think about these structures in terms of the unit cells, and shown on the left are a couple of different depictions of that. So the simple cubic, what you end up with then in the simple cubic structure is, this is, I think, is the best picture of it. You just have one atom in each corner of the cube, and that's all you have. So if you were to take out a little piece of this here, the simplest unit would be the one that has just one atom in each corner. What this is showing below that is if we take those unit cells and then start stacking them in all directions, you get this more complicated lattice. So that's what this is showing. And the bottom one here that's often helpful to think about is sort of the space-filling model. So the atoms, again, are going to stack as close to each other as they can. So basically the electron density, or the electron cloud of those atoms, are going to come as close to the next one as they possibly can. And so what you really get in these structures is sort of this picture here, where all the atoms are adjacent to each other, occupying as much of that space as possible. So the diagram on top is easier to visualize because it's a lot clearer where those atoms are located, and shows the very simple depiction of one little atom, one sphere in each corner. But in reality, it's going to look more like this, and we do have to sometimes think about that space-filling model where you have all of the available space from the atoms all touching each other, as close to each other as they can possibly get. So that's the simple cubic structure. Also called primitive cubic, I should say. So if you see the word primitive, that means the same thing as simple cubic. So there's sometimes two names for these depending on different sources and things, so don't get confused by that. So that's called the primitive cubic or simple cubic structure. Now what I'm going to go through now is some geometry to talk about some various aspects of this. So we're not going to hold you responsible for all of this information, but there are a key few pieces of information on here that we want you to at least understand and be able to reproduce on the test. So what we're doing in this is we're taking one face of the cube. So if we go back to this picture here, we're just taking one of these square faces of the cube and looking at it in 2 dimensions. Okay? And as we said, the atoms, which are represented by these spheres, or these little quarter of circles in this case in the 2-dimensional slice, are all touching each other. So as you go along one length of the cube here, what we call the length of a side is A. Lowercase a means the length of a side. In a cubic structure, hopefully you guys are all familiar with the definition of a cube. In a cubic structure, you just have all the lengths are the same side, all the edges are the same, and all 90-degree angles. That's what a cube is. So we have this side length A that defines the size of the unit cell. And then as we go along one of these side lengths, we'll see that we go through one atomic radius from this atom plus one atomic radius from the atom next to it to go through that side length A. So what that means is the length of a side A is given as 2r. Eventually. So A equals 2r. The length of one side is equal to 2 times the atomic radius of whatever atom is making it up. So here r is atomic radius. Or for metal structures like we're dealing with, sometimes called metallic radius, but it means the same thing. It's the same atomic radius we talked about earlier in the course. So the side length A is equal to 2 times r. I'll put little check marks next to things that you should probably know for the test, because as I said, not all this stuff is going to be that important, but we're just kind of going through this. And the rest of what I'm going to derive here then is going to be just geometry. So I'm assuming most of you or all of you took geometry in high school, so think back to the good old days of whatever year that was. For me it was, I think, first year of high school, but anyway, we had all these different relationships now. So if we want to take the volume of one of the unit cells, the volume of one of those cubes, remember that the volume of a cube is just given by a cubed, where a is the length of a side. And then we said that a is equal to 2 times the radius, so in terms of the atomic radius, the volume of the cube is going to be 8r cubed. So that's the total volume of space that the unit cell takes up. Now let's think about how many of these spheres or atoms there are in one unit cell. And this is where we have to use those counting rules that we learned a little bit earlier. So in a simple cubic unit cell, going back to the full picture, we see that all 8 corners have an atom in them, and that's all we have for a simple cubic, right? So we have 8 corners, all occupied, and then each of those, remember, is shared by 8 unit cells, so that each count is 1/8. So these are the corner atoms that are occupied in a simple cubic. So in net, we just have 1 atom per unit cell in a simple cubic structure. All 8 corners, each one counts as 1/8, so there's 1 atom per unit cell. And then the other thing we can figure out is we determined above what the volume of the entire unit cell is, the cube that makes up the unit cell, 8r cubed, or a cubed. Now, what's the volume of the sphere then that is included in that unit cell? The volume of a sphere, we have 1 atom in the unit cell. And the volume of a sphere is, remember from geometry, 4/3 pi r cubed, where that's the same atomic radius r, the radius of the atom that makes up the unit cell, or the whatever the substance is. So it's just 4/3 pi r cubed. All right, so that, again, we're not going to necessarily, this you should definitely know also how to count the number of atoms in a unit cell. That's very important for a lot of the problems you'll see in the homeworks and on the test. And then the volume of spheres is 4/3 pi r cubed. So then what we can do is define what's called a packing efficiency. So one thing we're going to use to compare the different types of cubic structures is what percentage of the total volume is actually occupied by the atoms, right? Because when you stack spheres into a cube, there's going to be some empty space, right? There's always, you can see these little gaps here. You can't possibly fill all of the available volume. So we want to define a packing efficiency, which is the percentage of the volume that's actually filled in this cubic unit cell. So the way we define that is we take the volume of the spheres, or the atoms, which are what these spheres represent, divided by the volume of the cube, and then multiply by 100 to get a percentage of volume that's occupied by the spheres. All right? And so as we saw here, the volume of the spheres is 4/3 pi r cubed. There's only 1 net sphere in the whole unit cell, and it's 4/3 pi r cubed. The volume of the unit cell was 8r cubed. And so when we simplify this down, we get pi over 6 times 100, which is 52.4%. So that's the packing efficiency of the simple cubic unit cell. That means 52.4% of the volume is actually occupied by the atoms that make up that unit cell. This number, I don't think we typically test you on the exact numbers, but you're going to want to know the relative ordering of the 3 unit cells that we talk about today. So this is the first one, simple cubic, 52.4%, so we'll want to keep that number in mind as we compare to the other ones. All right, so that's some of the key features of the simple cubic unit cell. The next one that we have is called BodyCentered Cubic. So if we're going to generate this from a layer of atoms, it's a little bit different than the first one. So if we want to start with two-dimensional layers and then stack them on top of each other to get a body-centered cubic structure, the first thing we do is we place the atoms in a layer, but we leave a space between them this time. So remember in the previous example, all the atoms were sort of touching each other, next to each other in the layers. But we're going to place the atoms in a layer with spaces in between. Then we're going to take a second layer and we're going to stack it over the gaps in the first layer. So we're not going to stack it directly on top of the first layer. We're going to sort of slide it over. We're going to not eclipse it, but we're going to stagger it with respect to the first one. And the second layer is going to cover the holes that were present in the first layer, the gaps that we left unintentionally. Okay? And I'm showing these in different colors so we can easily see the different layers. In a metallic structure, these are all the same atom. It's just one type of atom. But we're just showing you the different colors to represent the different layers that you can use to make these structures. So the second layer is identical to the first, but we stack it in a staggered fashion. So we stack the second layer over the spaces in the first. And then finally, the third layer is going to go directly above the first layer, again filling in the spaces that were present in the second layer. So this we're going to stack the third layer so that it eclipses the first. So this type of structure has sort of an alternating stacking arrangement. You stack one layer, you stack the next layer in the gaps of the first layer, and then you go back to the original position and just stack them over and over again like that. So if we take out the simplest cube then that comes out of this, the unit cell that would result from this lattice, what we get is what's called a body-centered cubic structure. Okay? So in a body-centered cubic structure, you still have one atom in each corner of the cubes. As I said, that's always going to be the case for any cubic unit cell. But we also have one right in the center of the cube here. Okay? Maybe easier to see down here. You have the 8 corners filled, and you have this one directly in the center of all those corner atoms as well. And the lattice that results from that looks a lot more complicated now because you have, again, those sort of center atoms in between all the cubes. So it's hard to sort of visualize this extended structure. But if you look at one cubic unit cell, you see it's 8 corners plus 1 in the center. That's kind of the essence of this. Now, from a geometric standpoint, this one is a little bit more complicated now because the spheres are sort of touching each other along the diagonal of the cube. So if we want to go through 3 spheres that are actually touching each other, the spheres no longer touch each other along the edge of the cube. You can kind of see in this case that there's a little bit of a gap there. Not obvious, but there's a small gap in between them along the side. So if we want to go through atoms that are actually touching one another, we have to go through the diagonal of the cube from one corner to the other like that. That's all right. So this is what this picture is going to show then. So this red line here. Let me try to draw a better label to it. This red line here is a cube diagonal now that we're going to have to consider to think about packing efficiency and things for this. So this is a little bit more complicated then. So if we want to find the length of the cube diagonal, it's going to be from geometry. The length of the diagonal, d, is given by, or d squared is a squared plus a squared plus a squared. So this is sort of a 3-dimensional Pythagorean theorem if you want to think about it that way. So that's the length of a diagonal, and that's the length of each of the sides, which are all the same for a cubic unit cell. So what that means is that the length of our cube diagonal is given by a square root of 3. All right, so this red line here is given by a radical 3. It's the length of the cube diagonal, again, from one corner to the opposite corner across the whole center of the cube. Now, as we go through that, sorry, what's the question? All right, so that's d is equal to a radical 3, and the cube diagonal has that length. And then if we want to find the length of a side, what we'll see is that this cube diagonal, which is a square root of 3, as we go through this diagonal, we're going to go through one atomic radius for the corner atom. We're going to go through the center atom, which would be right here in the middle. That's another r. and another r, so 2r for the center atom. We're going through the whole diameter of the center atom, and then to get to the last corner, we go through the radius of the opposite corner atom. So we have to go through a total of 4r to get through that diagonal. Again, this is the hardest one to visualize, so some of this won't make total sense, but what we end up with is A is equal to 4r over square root of 3. So again, what we want to do is define the side length A in terms of the radius r, and it comes out to 4r over square root of 3 for this. So the geometry is a lot more complicated, but if you are fresh on your geometry, it should make at least a little bit of sense. And then finally, the number of spheres in the unicell. This is the one that we should be able to do for sure. It's a lot more straightforward. So in this type of structure, going back to the picture, we again have all 8 corners occupied. That's going to always be true for a cubic unit cell. So we have 8 corners, and those count as 1/8 each because they're shared by 8 unicells. We have 1 atom in the center that we have to count as well. And is that shared with any other neighboring cells? So no, that one is not shared. The one in the center of the cube does not get shared by any neighboring cubes because it doesn't overlap with any of them. So that's going to count as a full one. So we count the body center as a full atom, one of those, and it's completely occupied. So in total, we would have 2 atoms per unit cell, and that one you should definitely know how to do the math also to get there as well. Okay, so for a body-centered cubic structure, it's a total of 2 atoms per unit cell, 1 in net from the corners plus the one in the center. Okay, and then the volume of the atoms is going to then be, there's 2 of them in the whole unit cell times 4/3 pi r cubed. So each atom has a volume of 4/3 pi r cubed. There's 2 of them, so the total volume of the atoms in the unit cell is 8/3 pi r cubed for this. And then for the packing efficiency, we're going to take again the volume of the spheres or the atoms and divide it by the volume of the unit cell, which is given by A cubed. Okay, so we take the volume of the spheres, which is 8/3 pi r cubed. We divide it by A cubed, which is A is given by 4r over square root of 3. We cube that, so that's the volume of the spheres, that's the volume of the cube. So we can subtract or divide out the r, so we get 8/3 pi, and multiply the whole thing by 100, I should say. Sorry. 8/3 pi over 4 over square root of 3 cubed times 100. So what that comes out to numerically is 68%. All right. And again, whether we test you, I don't think we're going to test you on the exact numbers, but we should recognize that this one is more efficient at packing than the previous one. So the previous one, only 52% of the volume was occupied by the atoms. In this case, it's 68% because we've jammed a whole other atom into the center of the cube to be able to do that. So we get 68% packing for the body-centered cubic structure. Okay? Any questions on this one or the previous one? I didn't really stop. But all right, so that's the first 2, and then the last one is face-centered cubic. This is the hardest one to visualize from a layering perspective, but the easiest one to but not the easiest, but one of the easier ones to visualize in terms of the cubic unit cell. So in terms of how we use this how we use layers to generate this structure, another synonym for face-centered cubic is called cubic closest packed. And the reason it has this name is because the layers that we're using to generate this structure have the atoms as close to each other as possible, packed as tightly as they can for one 2-dimensional layer. So think about if you had a collection of marbles all the same size and you wanted to arrange them as close as each other as possible on a table, this is how you would do it. So each layer in the cubic close pack structure, you take one row of atoms, and then the next one is going to be staggered relative to that and fill in the little gaps in the first layer. So this is what's called a close packed layer. So that's what we start with. So you start with a close packed layer of spheres, which is what each individual layer looks like this here. And then the way we stack them is we take one layer which we'll label A. So the yellow layer at the bottom is going to be labeled A. The second layer is going to be stacked over the little triangular crevices in the first layer. So if you look at this layer here, that you have these little, let me do it in a different color so you can see it better. These little triangular crevices there, the little gaps that are in between the atoms. So the second layer is going to go right on top of those, right above those. So we call that layer B, so that's A. Then the second layer, which is in blue-green, is going to be called layer B. Go back to blue. That's layer B. Third layer goes over the cracks in the second layer, so then that's going to be layer C. And so we have what's called ABC or ABCA packing. So basically you stagger the layers twice before then going back and repeating them. So this fourth layer is another A layer, which is directly on top of the original A layer, or directly above it, I guess. Not touching it, but on top of it. So this is what's called A, B, C, A arrangements. So you stack the layers, stagger them twice, so a total of 3 different layers before then repeating the first layer exactly on top of it. So these 2 A layers are directly on top of each other, but they're separated by 2 intervening layers that are slipped relative to each other. So this is, again, the hardest one to visualize from a layering standpoint. What you should be familiar with is that this is called ABC or ABCA sometimes packing, which basically means you have 3 different layer stackings before you start repeating it over and over again. Okay? Now it's hard to translate this picture into the picture of a cubic unit cell because, as it turns out, these layers actually go along the diagonal of the unit cell. So to take a slice out of this that's a cube and define it as a cubic unit cell, we have to look along the diagonal. So again, this yellow one here is A, the green one is B, I think it's the other way. Yellow is A, the blue is going to be our B layer, green is C as I've labeled it above. So to really think about this in terms of a cube, it's really along the diagonal of the cube, so it's hard to visualize from that standpoint also. But what you want to be familiar with, even though the packing is kind of hard to visualize, is I would say this picture here is the best one to show, which is, as the name implies, face-centered cubic unit cell. We have 1 atom in each corner, and we also have 1 atom at the center of each face. So remember, there's 6 faces in a cube, so each of the 6 faces is going to have an atom right in the center of it, also shared with the unit cell that's next to it. So face-centered cubic has 1 atom in each corner, 1 atom in each face. Okay? So, and it comes from this sort of complicated stacking arrangement. As long as you know that it's called ABC or ABCA, that's the sort of most detail you'll need to know about that aspect of it. So that's what the face-centered cubic structure looks like. And so again, what we can do then is take out one of these faces and then define some things in terms of the atomic radius r. So in this case, we can again just look at a single face. We don't have to look at the diagonal, which makes the geometry a little bit easier than the last one. So if we go to the face-centered cubic structure, this is one of our faces, again defined with side lengths of A. And so if we want to go through, again, there's gaps between the atoms along the side, but if we go through the face diagonal in this case, we go through 3 touching atoms, 3 atoms that are all adjacent to each other. So we go through 1 atomic radius of that corner atom, 2 atomic radii of the center atom in the face, and then 1 atomic radius of the corner, so a total again of 4r. But this time it's not along a cube diagonal, it's along a face diagonal. So a face diagonal is, from Pythagorean theorem, just a squared plus a squared equals d squared, or the length of diagonal d is equal to a square root of 2. Alright, so d is equal, the diagonal is equal to a square root of 2, because this time we're talking about a face diagonal, not a cube diagonal. And we see then that this diagonal a radical 2 is equal to 4 times the radius, because as I said, we go through 4 atomic radii to get from one corner to the other along the face of a cube. So a radical 2 equals 4r, which means that a in terms of radius is equal to 4r over square root of 2, or more simply 2 radical 2r. Alright, so in this case, which I think that one, there could be some homework questions about, the length of a side A is given by 2 times the square root of 2 times the radius. So it's slightly more complex arrangement. The important one for us at this stage is to count the number of atoms in the unit cell, number of spheres. So if we go back to the picture, as we said, we again have each corner occupied. That's going to be true for all the cubic structures. So we have 8 corners, each counting as an eighth. And then, as we also said, we have all 6 faces have one right in the middle of the face. So there's 6 faces in a cube, and then each of those counts as what from earlier? Those all count as 1/2. Each face is shared by 2 adjacent unit cells that stack next to each other. So those are the faces, 6 times 1/2. So that means in net, the face-centered cubic structure, we have 4 atoms per unit cell. And again, you should be familiar with how to count this and and the mathematics that we use to get to that as well. All right. So that means the volume of the atoms or the spheres in the unit cell is going to be 4 spheres, each with a volume of 4/3 pi r cubed, which is 16 pi r cubed. 16/3, sorry. 16/3 pi r cubed is the total volume of the atoms in the unit cell. And then the packing efficiency is again given by the volume of the sphere, 16/3 pi r cubed, divided by the volume of the cube itself. So each side length is 2 square root of 2r. So 2 radical 2r, the whole thing cubed, will give us the volume of the unit cell, multiplied by 100 to get it into a percentage. So this comes out to 74.0%. Let me put a percentage next to it, sorry. All right, so the packing efficiency in face-centered cubic is 74%, so that's the most efficient packing. Another reason why we call it cubic closest packed. It's the closest packing we can get. And there's no other known cubic crystal structure that would have a packing efficiency higher than this. Okay, so we have 3 different cubic structures. We have simple cubic, which is the lowest efficiency, body-centered cubic, which is intermediate, and this is the most efficient packing of atoms in a cubic unit cell. All right. So that's what we come up with for this, for face-centered cubic. Some of the key parameters, again, being the number of atoms in the unit cell as well as the packing efficiency, the 2 that are most important to consider. The last one we'll talk about, but only in very brief detail because it's a lot more difficult to visualize, so we're not going to hold you responsible for much about this, is the hexagonal close-packed structure. So the way we generate this is actually we use the same types of layers that we use for cubic close packing, but instead of doing ABC packing, we do ABA packing. So in other words, what we do for that is we take the first layer A, we stack the second layer B on top of the cracks in the first layer, so that's our B layer, but then right after that we're going to repeat the A layer immediately. So it's not going to be staggered twice, it's going to be just staggered once and then repeating. So it's just 2 repeating layers, AB, AB, and so on. All right. So the hexagonal structure, the only thing you really need to know about it, or there's really only 2 things. One is that it's generated by AB or ABA packing. So it's the same types of close packed layers. So we're still using close packed layers for hexagonal, but we're stacking them differently this time. Instead of doing ABC, we're just doing AB packing. And then other things that we should be familiar with, we're not going to really derive in much detail, is number of atoms. This one I don't think we'll ask you about, but I'll just give it to you for completeness. So it's different than a cubic structure. So in this case, if we look at a top view of this structure, we have these 6 atoms on the top face that are going to be shared by 6 other unit cells. So now we're thinking about stacking hexagonal faces. So each of these is going to be shared by 6 adjacent unit cells. So it's going to count as 1/6. And there's these 6 on the top face. There's also 6 more on the bottom face down here. So there's a total of 12 atoms that are going to be shared by 6 unit cells. So those are going to be what we call the corner positions. And then what we also have is going to be 3 atoms that are completely in the center. So it's a little bit hard to see in this view, but there's going to be these 2 blue ones plus 1 behind it. That's completely in the center of the unit cell. And then we have these 2 on the top here and 1 on the bottom that are going to be shared by 2 that are stacked next to each other. So we don't have to worry about how to derive this. We're not going to hold you responsible for counting in hexagonal structures because it's more complicated. But the whole point is that in net we have 6 atoms per unit cell in a hexagonal close-packed structure. All right, so that number might come up, but we're not going to hold you responsible for the derivation of that number. The other thing to be familiar with is that the packing efficiency for this is identical to cubic close-packed. Okay, so even though it's stacked differently, we end up with the same exact packing efficiency. We're not going to derive that because the geometry of hexagonal prisms is more complicated than I wish to get into, or probably could get into even if I tried. So we're going to leave it at that. That's all we really need to know about hexagonal close packing, is that it's just a different type of stacking, same layers but different stacking than the cubic close packed. 6 atoms per unit cell, packing efficiency of 74%, same exact packing efficiency as well. Okay? So those are the 4 major structure types, the cubic ones being the ones that we're going to ask you the most about on homework assignments and tests, as you'll see. The last thing to define is what's called coordination number. So coordination number is the number of nearest neighbors in a crystal structure. So each atom is surrounded by some other number of atoms that are next to it, and that number of nearest neighbors is what's defined as coordination number. Another way to think about this is the number of other atoms that an atom is touching in a crystal. All right, so it's the number of other atoms that an atom is touching in a crystal. So how many is bounded by, how many is closest to. Okay, so that's called the coordination number, or number of nearest neighbors. And those numbers are going to be different for all four of these crystal structures. So if we go to the simple cubic structure, remember that the layers for a simple cubic structure look like this. So if we focus on this atom here and figure out how many atoms are touching that one, we can count those. We have 1, 2, 3, 4 that surround it in the same plane. So those 4 surround it in the same plane, but we also have one above and one below. Because remember, to generate the simple cubic structure, we would take this layer and we'd stack them on top of each other. So this atom here is going to have one atom from a layer above it that's right next to it, one atom from a layer below it that's right next to it. And so what we get then is a coordination number of 6. All right, so the coordination number, or number of nearest neighbors for simple cubic, is 6. The other way to see that is to look at this atom here in a simple cubic lattice, and we see that it's going to be surrounded by 1, 2, 3, 4, 5, 6 that are all closest to it. It's a little bit harder to see in that viewpoint, but that's another way of seeing that there's 6 nearest neighbors for any atom. And since we're stacking them all the same in all directions, every single atom has the same coordination number of 6. For body-centered cubic, the easiest way to visualize this is to just look at one unit cell. And so if we look at the center atom in the unit cell, we can figure out how many atoms are closest to it. Those are just going to be the corner atoms that are surrounding it. So how many corners are there? There's 8. So 1, 2, 3, 4, 5, 6, 7, 8. So the coordination number in body-centered cubic is 8. And that's true for every atom in the structure. So when we stack this in all directions, every atom is going to have 8 nearest neighbors for body-centered cubic. And then the last one for the close packing structures is, again, a little bit harder to visualize. So what we'll see for this one is that if we focus on, let's say, this atom here in the structure, in the same layer there's going to be 6 that are all surrounding it. Okay, so we have 6 from the same layer that are all nearest neighbors. But then remember that when we're stacking these, we also are going to have some above and some below. So let me try to draw those in. So right below it we have these 3 that are right below it in the layer below, and then we have 3 in the layer above, which would be 10, 11, 12. All right, so the coordination number for body-centered cubic is going to be 12. There's going to be 6 in the same layer, 3 in the layer above, 3 in the layer below. Coordination number 12. Again, you don't have to worry about deriving that or picturing that in any level of detail. Just remember that the coordination number for that is the highest, and that would also be true for hexagonal close packing as well. They have the same coordination number. So also, the coordination number is different between the 3 structures, 6, 8, and 12 for the 3 cubic structures that we talked about. All right, so any questions on cubic structures? So the last thing that I'll do for you then is a quick summary. So this gives you kind of all the information you'll need in one convenient table, so you don't have to worry about a lot of the background. So we have 4 different structure types, the 3 cubic ones and the hexagonal one. The names, we have simple cubic, which is sometimes also referred to as primitive cubic. All right, so we saw that simple cubic is also called primitive cubic. So we just want to make sure we're familiar with all the possible terminology. Body-centered cubic doesn't have a synonym, but it's abbreviated as BCC, body-centered cubic. So if you see that abbreviation, that's what that refers to. Face-centered cubic has 2 abbreviations and 2 names, FCC for face-centered cubic, or CCP for cubic closest packed. So there's, again, two names for that one. Hexagonal, the abbreviation is HCP, hexagonal closest packed. All right, so those are sort of the names and common abbreviations for those. As we saw, the number of atoms per unit cell is different for all of these. For simple cubic, it's 1. It's just 8 corner atoms. Each time's an eighth. 2 for body-centered cubic, 4 for face-centered cubic, 6 for hexagonal. So you should be familiar with the number of atoms per unit cell, as well as for the cubic structures, how to count these numbers. So where do these three numbers, 1, 2, and 4, come from? Make sure you're familiar with that also, based on the locations of the atoms and the rules that we have for counting. Coordination number we just derived. As long as you know the number, that's going to be the important thing. So that's going to be 6 for simple cubic, for some reason that stylus always putzes out about halfway through. So we have 6 for coordination number for the simple cubic, 8 for body-centered, and 12 for each of the close-packed structures. And what we see then is that there's a correlation between coordination number, which is how many nearest neighbors, how many atoms are surrounding one, versus the packing efficiency. So it was 52.4% for simple cubic, that's the least efficient packing, 68% for body-centered cubic, 74% for each of the close-packed structures. So we see there's this correlation between coordination number and packing efficiency. And like I said, we're not going to likely test you on these exact numbers, but you should know the order they come in at the very least. So one thing we're not going to really cover in this class, we might be wondering about is, why do we have these different structures? What determines, what metal is going to occupy these structures? We're going to give you some information about that for ionic compounds. For metals, we're not going to worry about that, but suffice it to say, the reason we have these different structures is because depending on the atomic radius, it's going to prefer one of these structures over the other. So atoms with a very large atomic radius, relatively large, can accommodate more nearest neighbors surrounding it, so they tend to favor these more close-packed structures, whereas really small elements tend to favor primitive cubic. But it's very difficult to predict what structure a certain metal will occupy. There's not really an easy way to predict that for metal structures. It's also sort of a big mystery to a lot of people. Why is, face-centered cubic and hexagonal have exactly the same packing efficiency? So how does a structure, how does a metal decide which of those structures to occupy? That's something that I don't think anybody really fully understands. So there's not anything really more we're going to say about that. But there are these different structures that commonly exist for metals. There's others that we won't talk about in this class. We want to be familiar with some of the structural features of them. Okay? All right, so this, we'll do one sample problem. Probably more complicated than you'll see on any homework assignment or exam, but if you can follow this and understand it, it really would show that you have a pretty firm grasp of a lot of things that we talked about today. So if we give you the structure of a metal and some of the other features about it, like its side length A, we're going to show you here that we can calculate the density of that metal in grams per cubic centimeter. So one of the key physical properties that's related to this type of structure that a metal occupies is what the density is. So we're going to do that for this one. So remember that density is given by mass over volume, which what we need then is we need the mass of sodium in the unit cell in grams divided by the volume of the unit cell in cubic centimeters. All right, because we have the information that we need to do this based on the structure, which is body-centered cubic, and the length of the unit cell A, which is 429 picometers. So the first thing to do is think about the counting. So for body-centered cubic, we have all 8 corners occupied, plus we have 1 in the center. So as we said, there's 2 atoms per unit cell in 1 unit cell. So 2 atoms of sodium in 1 unit cell. So that's how we count the number of atoms per unit cell. So if we know that there's 2 atoms per unit cell, how to figure out the mass of 2 atoms of sodium? That's just going to be some mole conversions like we learned back in chapter 5. So the mass of sodium then is going to be, we have 2 atoms. How do we convert number of atoms to moles? Here's some mumblings. Did anybody see Avogadro's number, hopefully? Good. So we're going to use Avogadro's number to convert number of atoms into number of moles. So 1 mole of sodium in Avogadro's number of sodium atoms All right, so that's moles of sodium, and then we use its atomic mass to find out how many grams that corresponds to. So the mass of sodium in this unit cell is 7.64 times 10 to the minus 23 grams. I hope I got the exponent right on that. That sounds, is it minus 23 or minus 22? I hope I didn't screw that up. I think that's right. All right, so then the volume of the unit cell is going to be, remember, for a cube, we take the side length, A, which is 429 picometers, and we cube it. So the volume of the unit cell is going to be 429 picometers cubed, which is 7.90 times 10 to the 7th cubic picometers. But we want the density in grams per cubic centimeter, so we need to do some unit conversions to get this number, this volume, into cubic centimeters. So the volume in centimeters cubed is 7.90 times 10 to the 7th cubic picometers. Remember that 1 meter is 10 to the 12th picometers. That's not a unit that we use all the time, but it's 10 to the 12th is pico, or 10 to the minus 12 more accurately. But we have to cube that whole thing because it's a cubed unit. So it's 1 meter per 10 to the 12 picometers, whole thing cubed, to go from cubic picometers to cubic meters. And then to go to cubic centimeters, it's going to be 100 centimeters in 1 meter. So I'm doing this as a two-step conversion to go from picometers to meters and then meters to centimeters. We have to cube both of the conversion factors because we're dealing with a cubed unit here, a volume unit. And so that comes out to 7.90 times 10 to the minus 23rd cubic centimeters. And then finally the density is going to be, I'm running out of room of course, density is the number of grams that we calculated, 7.64 times 10 to the minus 23rd grams, divided by the volume, which is 7.90 times 10 to the minus 23rd cubic centimeters. Which is 0.967 grams per cubic centimeter. So that's the number we would calculate. All right. And then if we went to Wikipedia and looked up the density of sodium, which is perhaps a little bit faster than doing it this way, what we would find is that the density is basically identical to that, 0.968. So we can use crystal structures to predict the densities, which we can also measure independently, and they match up quite well with each other. So this gives you an idea of how we can use information from a crystal structure to determine density. Again, that's beyond what you guys are going to have to do for any homework or test questions, but if you can at least follow the steps in this, you could be more confident you understand this. All right, the next couple things we're going to talk about are other types of crystalline solids. We're not going to give you as much detail about their structures, but just some of the key features of them. And the big thing you're going to have to do on the test, which we'll summarize at the very end of today, is how to classify different structure types as metallic or ionic or the couple that we're going to learn today. So the first one we're going to talk about is what's called a network solid. So these are also extended solids, but they're formed not by metallic bonds but by covalent bonds. So they're extended solids, but they have covalent bonds. And what you can think about these is, previously in this course we talked about covalent bonds as being involved in the formation of molecules. These network solids are basically infinite molecules. They're just molecules that have bonds that go on and on and on in all directions forever. So these can be thought of as infinite molecules. They're just covalent bonds, but they don't have sort of these discrete molecules. They just have this extended continuous structure that goes on infinitely. So because these are formed by covalent bonds, these are going to only involve non-metal atoms. They're not going to involve any metals. These are all covalent, either elements or compounds. And so the two elements that commonly are involved in this is going to be carbon and as well as the ones below it. So carbon, silicon, germanium, some of those group 4 elements would all be classified as network solids. And carbon has two different forms, which are both classified as network solids or network covalent solids. Okay. So the first one is called diamond. So these are tetrahedra of carbon atoms. Sorry to spell that right. So if you look at each carbon atom in this structure, it's going to be bonded to 4 other carbon atoms, 1, 2, 3, 4, and then each other carbon atom is bonded to 3 more in each direction. So basically you just have this continuous network where each carbon is bonded to 3 other carbon atoms in all directions. Okay. So because the carbon atoms are tetrahedral, what's the hybridization going to be? sp3. Okay, so it's sp3 hybridized for each carbon atom because they have 4 things bonded to them. So they have hybridized 4 atoms, and these are going to be all sigma bonds. You can't have pi bonds when you have sp3 hybridization. So that's one type of network solid for carbon, which is called diamond, the most valuable of the two. The other type is called graphite. So in graphite, what you have are hexagons of carbon atoms in stacked layers. Sorry, stacked in layers is probably a better way to say that. So in this case, each carbon atom is bonded to 3 others, all in the same layer. So you have sort of these 2-dimensional layers that go on in all directions, and those 2-dimensional layers are stacked on top of each other and held together by van der Waals forces. There are no bonds between the layers. All the bonds are within a single layer. And then you have these London dispersion forces, I should call them. That's the more accurate way to say it in this course. These London dispersion forces hold together the individual layers of carbon atoms, so there are no bonds between the layers. And because the carbon atoms are each bonded to 3 nearest neighbor carbon atoms, what's the hybridization in this case? sp2 is bonded to 3 things. So we have sp2 hybridized carbon atoms, and this time we have sigma and pi bonds. So you have sort of these directional sigma bonds between the carbon atoms that are all in the same plane, and then you have pi bonds that are delocalized above and below that plane, sort of like we have in that benzene molecule, but this time it extends in all directions in 2 dimensions. So that's what we have in graphite. The properties of diamond and graphite are very different, as you're likely aware. So diamond is an extremely hard, clear, solid, colorless solid. Graphite is sort of black and slippery and soft. So the physical properties are very much different between these two because of the different types of bonding that we have. One definition to be aware of that's appropriate here is what's called allotropes. So these are 2 forms of the same element. And so diamond and graphite are considered 2 different allotropes of carbon. So graphite is the standard state of carbon. So when you talk about the standard state of carbon as graphite, that's the most stable one at 25 degrees Celsius and 1 atmosphere of pressure. But diamond is another allotrope that can exist. So I don't remember if I mentioned this to you before, but you have these 2 allotropes of carbon, diamond and graphite, and actually graphite is the one that's the more stable of the 2. And so what that means, if you have a diamond and you let it sit there for millions and millions and millions of years, it will eventually convert into graphite. So the saying that a diamond is forever is false, chemically speaking. So the diamond companies have been lying to you for your whole lives. Graphite is a more stable form, but it takes, as I said, an extremely, extremely long amount of time for that to happen. So I guess at least in the time scale that we expect to be alive, a diamond is forever. All right, so those are the 2 forms of carbon, and both of those are examples of network solids. They have covalent bonds extending in all directions and forming these extended structures, but this time through covalent bonds, not through metallic bonds. So as I already sort of alluded to, the properties of these are very different because of the different types of bonding that they have. So diamond is hard, it's colorless, and from an electrical standpoint, it's an insulator. But then in graphite, you have different physical properties. It's soft and slippery. The slippery nature is because, as I said, the individual layers are just held together by London dispersion forces. so it's very easy for the layers to sort of slide over each other in graphite. It's not colorless, as you know, it's black. They used to make pencils out of graphite, but I don't think they use it as much anymore. And electrically, it's actually a conductor of electricity. So it's a rare example of a non-metal that conducts electricity. Now, what's the reason for these differences, especially with respect to their conductivity? What we want to start understanding is what's called band structure. We're going to see this both for these types of substances as well as for one other class that we're going to see in the next slide. So band structure is basically the idea that, remember when we talked about in Chapter 4 molecular orbital theory? When you form bonds between atoms in a covalent bonds, you're going to form bonding orbitals that are lower in energy and anti-bonding orbitals that are higher in energy. And the same thing is going to happen when you have these extended structures, these network solids. You're going to form orbitals that are bonding, that are lower in energy, orbitals that are anti-bonding, that are higher in energy. But this time you get a lot of those, right? Because you have, infinite number of atoms in the structure, so you're going to get tons and tons and tons of orbitals. And what they actually do is these orbitals tend to sort of stack close to each other in what are called bands. And so the way to think about this then is for insulators like we have for diamond, you have your filled bonding molecular orbitals down here. And these are typically the bonding ones that are going to be filled in the ground state. This is what we refer to as the valence band. So that's kind of the terminology that's used for extended structures, is valence band. We don't call them bonding orbitals or filled orbitals. We call them the valence band. And then up here at higher energy, you have your empty molecular orbitals, the ones that are not filled in the ground state. And this is called the conduction band. And in anything that's an insulator, you have a pretty large gap between them. Because in order to have electrical conductivity, you need electrons to move around. And if all of the electrons are down here in these filled molecular orbitals, the only empty places for them to move are the empty ones up here. Those are really high in energy, so it requires a lot of energy for those electrons to go into the conduction band. So when you have an insulator, you have a large gap between valence and conduction band, and it's not very easy for the electrons to move between them, which is what you need for conductivity to be observed. So that's what you have in insulators. And then if we go to, so most nonmetals are insulators, as we said, and diamond being a classic example of that. But if we go to things that conduct electricity well, which would be metals, and graphite is the sort of exception to a nonmetal that is conductive. So metals and graphite are all considered conductive. And what happens in this situation is that you have a very small gap, or almost no gap, between the filled and empty molecular orbitals. So you have your valence band, which is going to be shown here in blue, and then your conduction band, the empty molecular orbitals, are basically right next to that with no or very small gap between them. So here you have no band gap, no gap between the valence and the conduction band. Okay? So that's what the picture looks like for things that conduct electricity. You have the valence and the conduction band right on top of each other. It's very easy for the electrons then to move between the valence and conduction band, and so you get this free movement of electrons that leads to electrical conductivity. And the reason why diamond and graphite are different is, again, think back to molecular orbital theory. So if we formed a sigma bonding and a sigma anti-bonding orbital, that would have a pretty large gap between it, but a pi bonding and a pi anti-bonding have a smaller gap. Remember that the distance between the bonding and anti-bonding orbitals depends on how strong the overlap is. So sigma overlap is very strong. You get a large gap between bonding and anti-bonding, which leads to a large band gap in diamond. But when you have graphite, the frontier molecular orbitals are all pi orbitals. As we said, there's pi bonding in graphite. The pi bonding and anti-bonding orbitals are much closer to each other. They don't split nearly as far, and so that shrinks the band gap and gives you electrical conductivity. So it's, again, that difference in bonding type, sigma versus pi, that leads to this difference in electrical conductivity for diamond and graphite. So we sort of saw here the difference between conductor and insulator. We also have intermediate ones, which are called semiconductors. So the classic examples of semiconductors, these are also network solids, but the classic example of this is silicon, the element Si. So in this case, you have an intermediate band gap. So you have silicon has the same structure as as diamond, but it doesn't have as large of a gap between its valence band and conduction band. So you have valence band, you have a conduction band in red. So valence band and conduction band. And in this case, you don't have a zero gap, but you have an intermediate gap between the two. So again, energy increasing bottom to top. So you have an intermediate band gap. And so the difference between semiconductors and metals is that, unlike metals, the conductivity increases as you raise the temperature. Come on. Always, my heart skips a beat every time that happens. I feel like something's going to crash. The conductivity for semiconductors increases with temperature, which is a difference between semiconductors and metals. And the reason is that in a semiconductor, in order to get conductivity, you need your electrons to hop over this small gap. And the higher the temperature, the more electrons have enough energy to hop that gap. So increasing the temperature in this case increases the average energy, the thermal energy of the electrons, and that gives more of them enough energy to hop over the band gap. Because remember, anytime you have conduction, or conductivity, you're going from the valence band to the conduction band. And so in semiconductors, increasing the temperature improves that. There are other types of semiconductors as well. So this is what would be called an intrinsic semiconductor up here, where you have just this sort of natural intermediate band gap. The other types are called doped semiconductors, which are either called N-type or P-type. So in an N-type semiconductor, you dope with extra electrons. So for example, let's say we had silicon as our host material. Silicon has 4 valence electrons, and so if we dope that with something that has more than 4 valence electrons, usually just 5, like arsenic, that would be an example of an N-type semiconductor. So arsenic-doped silicon is an N-type semiconductor. We're taking silicon, we're adding in a little bit of arsenic to give it some extra valence electrons. Now, we don't add a lot. The doping is usually a very small percentage, I think like 1% or less for most semiconductors. So you're just adding in a very small amount of arsenic into the silicon structure. And so the way this works then is you have your sort of intrinsic valence band and conduction band for the host material silicon. Which have their sort of characteristic band gap. But as we said, when you have N-type doping, you're putting in a little bit of extra valence electrons. So normally in silicon, the valence bands are completely filled, and that conduction band is completely empty. But now we have extra electrons from the arsenic that have to go somewhere. We fill the valence bands, so we can't add any more electrons to the valence bands. So we introduce sort of a new level very close to the conduction band that's going to be filled with those extra electrons. So you have these extra electrons that occupy a band very close to the conduction band, and those extra electrons can very easily hop into the conduction band, and that increases the conductivity. So this doping is a way of increasing the conductivity of a semiconductor by adding in new orbital levels that are close to the conduction band in this case, and allow the electrons to very easily move then into the conduction band. So that's called N-type doping. The other type is P-type, where you dope with fewer valence electrons. So an example of this would be taking silicon and doping it with boron. So silicon, as we said, has 4 valence electrons. Boron has 3, so if you dope silicon with boron, again, just adding a small percentage of boron into it, you're going to get what's called P-type behavior, boron-doped silicon, where boron has 3 valence electrons instead of 4, so you have fewer valence electrons. And the way the band diagram looks in this case is that you have your valence band and your conduction band again for silicon. But because it's doped with boron, we don't have quite as many valence electrons, because we're basically replacing some of the silicons with borons. So we're removing valence electrons because boron has fewer valence electrons than silicon. And so we introduce some holes, what are called holes in the valence band. And these holes denote positive, these are sort of positive charges or vacancies in the valence band. They're not real positive charges, but they're basically the absence of an electron. You're partially removing the electrons from the valence band. And because of that, you again have some gaps in the valence band, some places where electrons can now move into that are at basically the same energy level, so you have free movement of electron. So p-type is a little bit harder to understand, but you're basically removing electrons from the valence band, and that means the electrons that are there can move into those holes, and you have this sort of easier conductivity as a result. So those are the two types of semiconductors, which are also classified as network solids. The last type of network solid that we want you to know about is what's called a network covalent compound. And there's really only one example of this that you're going to be responsible for knowing. There are others, but if we think about a network covalent compound, now we have two different elements in the structure. So the network atomic solids that we saw, like carbon, graphite, and diamond, were just carbon atoms all bonded to each other. For a network covalent compound, as the name implies, it's going to be two or more different elements. So if we were thinking about CO2, remember that in CO2 we had a molecular structure with sort of this linear geometry with 2 sigma and 2 pi bonds. And it's a nonpolar gas. So those are sort of the properties of CO2 that we saw. So that's what we saw for carbon dioxide, 2 sigma and 2 pi bonds. Now, if we go to SiO2, silicon is just one row below carbon on the periodic table. So it'd be the same number of valence electrons. So we might expect, without knowing otherwise, that SiO2 is just another nonpolar gas. It's silicon with 2 bonds to oxygen, but things are actually a little bit different for SiO2. The reason is that in silicon, we're now using 3p orbitals, which form very weak pi bonds. So in carbon dioxide, you have 2p orbitals on carbon, 2p orbitals on oxygen. Those overlap very nicely to form pi bonds. But in SiO2, you need to use the silicon 3p orbitals, which form very weak pi bonds. And remember, when we form compounds, the goal of the compound, if you want to anthropomorphize it, is to form as strong of bonds as possible. So because the pi bonds between silicon and oxygen are weak, it's not going to form them at all. Instead, it's going to form 4 sigma bonds, which ends up being a more stable arrangement for SiO2. Now, how does it do that? Because it's only bonded to 2 oxygen atoms, how can it form 4 sigma bonds? It forms a network solid where you have covalent bonds being formed in all directions. So each silicon is tetrahedrally bonded to 4 oxygen atoms. So you have O, 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 and O. And then each oxygen is then bonded to another silicon, which is then bonded to 3 oxygen, more oxygens, and so on. So you have this, again, this network solid where you have covalent bonds going in all directions in these types of structures. So that's bonded to a silicon. This silicon is bonded to 2 more oxygen atoms if we want to keep drawing more pieces of the structure. That's bonded to another oxygen atom, which is bonded to silicon, and so on. So it just goes on forever and ever, this network solid, as we call it. All right, so all silicons are tetrahedrally coordinated, and they have 4 oxygen atoms bonded to each one, and it just extends forever. Now you're wondering, how does this work? Because technically these are, so it goes on forever, as I said. These are SiO4 2- tetrahedra that extend infinitely. So wouldn't the whole thing be negatively charged? Well, usually the surface atoms, the ones that are not part of the network, are going to be terminated by, for example, H+ or something to balance the charge. Okay, so you're going to have some, usually in silica, hydrogen in there, or you're going to have what are called surface defects that balance the charge. We don't need to worry about that, but basically we need to understand is that this is a network solid that forms covalent bonds in all directions between silicon and oxygen. All sigma bonds, no pi bonds in this case. So the properties of SiO2, it's a hard, sort of brittle solid. So hard, brittle might sound like 2 different things. It basically means it's not malleable. You can't bend SiO2. It basically crushes. It's a very common substance that you may be aware of. It's in sand and glass. So both sand and glass contain SiO2. As we said, glass is an amorphous structure, which would mean it would have this basic structure but no real regular repeating units, just kind of all random. There are also crystalline forms of SiO2 that would have very regular directionality to their structure, very regular repeating units. So SiO2 is really the only network covalent compound I want you guys to worry about. The last thing I'll go over, if you'll just afford me a few more minutes, is one important thing we're going to ask you to do on the test is to classify solids. Actually, I don't want to keep you guys late because I know some of you have to go. So I will cover this next time, but this will be the last thing that's going to be involved in the third midterm. Is just we have a few different structure types now. How do we distinguish between them? And that's going to be something you'll be expected to do on the exam. So we'll get that next time to wrap this whole section up before moving on to other types of solid-state structures.